Okay, so about that, you guys out there in Zoom. I don't know if you're able to follow what I was writing down. But if you have any questions, feel free to ask about what we have just done here. And I was just saying that based on what we have covered so far, you should be able to do questions 1, 2, and 2 has several sections. Okay, so questions 1 and 2 you should be able to do because we haven't done solubility product yet. That's what we're going to do next. All right. Okay, so I take it it's okay for me to clear this. So let me do that now. And let me go back to the PowerPoint. Okay, so let's talk about indicators. I think I alluded to indicators earlier. These are substances which takes on a particular color depending on the pH of the environment it's in. And these are basically dyes, right? And also they're basically weak acids or weak bases, right? Depending, all right? So just to explain how an indicator works, let's say we have this here which represents the acid version of the indicator, HIN, and it dissociates as a weak acid to form H plus and iron minus, right? So what you'll find is that this substance here, HIN, will have a different color compared to the conjugate base, right? And the one that predominates in the mixture is what basically determines the color of the mixture, all right? So just to use I'm just making up an example here. So let's say that the color of this indicator here, the undissociated molecule, okay, so let's say the undissociated molecule here, let's say the undissociated molecule here, let's say that the color of this is blue, and let's say for the conjugate base, let's say the color is yellow, right? So what happens is that if the solution is very acidic, right, a lot of acid present, then that would push the equilibrium to the left. And as a result, the blue-colored molecules will predominate compared to the yellow conjugate base ion. So therefore, overall, the solution will be blue. On the other hand, if the solution is, if you add a lot of base to it, the base would reduce the concentration of the H plus, and therefore the equilibrium will shift in the other direction, and therefore the yellow-colored conjugate base will predominate, and therefore the solution itself will be yellow, all right? Now, what you'll find in practice is that if the concentration of the undissociated molecule, like HIN, if its ratio to the concentration of the conjugate base is greater than or equal to 10, then the color of this will predominate in the solution. And the opposite is true if things are flipped. In other words, if the concentration of the undissociated molecule compared to the conjugate base is less than or equal to 10, then the color of the conjugate base, which is the iron minus in this case, would predominate as far as the solution is concerned. And here we have down below a list of different indicators and their color as far as what it would take on when it finds itself in either an acidic or basic environment. So just to highlight maybe 1 or 2 examples. This one, for those of you in my lab, you will encounter this one. In fact, you encountered this already actually when we did the experiment with the dissociation of weak acid constants. So phenolphthalein, its color is colorless in acid and pink in base, right? And what you'll find is that the changeover from one color to the other will occur from pH 8.3 to pH 10, right? So basically, between these 2 ranges, you would have a mixture of the 2, but below 8.3, the acid color would predominate, which would be the colorless color, and the reddish pink color will predominate above pH 10. And you see some other ranges for different indicators, all right? So these are just some common acid-base indicators, and they all behave according to what we just described here. Okay, and this is just basically showing you a dye that has been extracted from a type of cabbage. And basically what they have done is add acid and bases. Well, basically they add acid or base and they arrange them in order of increasing pH, and you see that there's a color change as you go from one particular pH value to another, right? So this is, you have some indicators. In fact, you have what is called the universal indicator, which gives you different colors over a particular pH range. And you even have indicators in the form of colored dyes that are, or paper that is soaked in dyes and dried. And basically, again, they are designed such as to measure certain pH values over pH range. And for those of you who are in my lab, in today's experiment, you're going to see how you can determine approximate pHs based on the color of the particular indicator. You'll be given a scale, a color scale, which gives you the corresponding pH values for different colors. And then you can dip your paper in that solution that you're trying to measure the pH of. You compare it to the scale to see what your approximate pH of the solution is, all right? So that's basically how these work. Indicators are very important because, especially when it comes to titration, we need to know when we get to, as I mentioned before, the equivalent point, the point where the moles of the base and the moles of the acid are stoichiometrically equivalent, right? So this illustrates the importance of the indicators in this type of experiment. So this is a titration curve for a strong acid and a strong base, right? And in practice, you need to find out where is the equivalence point, which would be at pH 7. We know it's going to be pH 7, but when you're doing the experiment, unless you have a pH meter reading the pH, the next best convenient way of doing it is by using the appropriate indicator. But the choice of indicator is very important, right? As you can see here, they're showing you the pH ranges for 3 indicators when they change from the acid to the basic color, right? You have thiamine blue, you have methyl red, you have phenolphthalein, right? You'll notice here that in the case of the strong acid, strong base titration, there's a big jump of the pH from 3 here to about 11 point something, right? So the indicator that you choose in order to indicate the equivalence point must change over color within that jump, right? So in the case of thiamine blue, the color change occurs before you get to that sudden increase. So therefore you would not use thiamine blue for this purpose, right? Because basically the color of the thiamine blue will change before you get to the equivalence point. You want the pH or the color of the indicator to change in the range of the pH of the equivalence point. And that would be so in the case of methyl red and also in the case of phenolphthalein. In both of these cases, you'll notice that the changeover in colors here and here would be within that big jump from, as I said before, 3 to about 11 point something, almost 12, all right? So therefore, in this particular experiment, the appropriate choice of an indicator would be either methyl red or phenolphthalein, but thiamine blue would definitely not be a good choice of an indicator to indicate the equivalence point of this particular titration, all right? So with that said, let's look at this example. This question says, which indicator would you use for the titration of nitrous acid with potassium hydroxide? The first thing you have to identify when answering this question is what type of acid and what type of base you're dealing with, all right? So nitrous acid, what type of acid is it? Is it a strong or weak acid? Come on, you guys should know by now. Nitrous acid, is it strong or weak? Remember, there are 6 strong acids. It would be weak acid, exactly. And what type of base is potassium hydroxide, strong or weak? Strong, okay. So basically, if you're titrating a weak acid versus a strong base, then what would you expect the pH at the equivalence point of this titration to be? Would you expect it to be above 7, below 7, or at 7? You're titrating a strong base with a weak acid. would you expect the pH at the equivalence point to be above 7, below 7, or at 7? Above 7, all right? So basically, you have to choose one of these indicators that would change over color within the pH range that is above 7. So of these indicators, which ones or ones would you choose to indicate the equivalence point for this titration? Which one changes over their change their color within a pH range above 7? I'm sorry? The last two exactly. Cresol red and phenolphthalein. All right? All right, so these are the two indicators you use for this type of titration. All right? If you choose any of the others, what will happen is that the color change will occur before you get to the equivalence point. Okay, so based on that, there is at least one question in the assignment that I gave you guys. Let me see if I can locate. Okay, so assignment. Okay, unfortunately, it's not, the questions are not in order, but the question you should be able to do right now is number 8, right? So it says in number 8, an indicator, HIND, is yellow in 0.1 m sodium hydroxide and blue in 0.1 m hydrochloric acid. And it says the pH range in which a color change occurs in this indicator is 3.6 to 5.2, right? So the question is asking, write the equilibrium equation describing this indicator. So basically the indicator is a weak acid. So what do you think the equation is? Excuse me. HIND, that's the indicator molecule. So what will happen when this is dissolved in water? It's a weak acid. So what would be the equation? Plus H2O to give what? So what would be the products of this dissociation? Sorry?
IND
IND what?
minus
Minus plus
H3O plus.
H3O plus. Okay, very good. All right. Now, the next question is, what is the color of the HIND and what is the color of the IND minus? Now, according to the question says, the hint lies in this part of the question. The indicator is yellow in 0.1 m sodium hydroxide and blue in 1 molar hydrochloric acid. So based on that information, what do you think the color of the undissociated molecule, the HIND, is? Well, okay, let me ask you this. If you add sodium hydroxide to this acid, to this indicator, based on the equation, which direction will the equilibrium shift if you add sodium hydroxide? What will the sodium hydroxide react with in this system right here? Or more specifically, what will the hydroxide ion react with in this system right here? The hydronium ion, right? So it's going to react with the hydronium ion. So therefore, the concentration of the hydronium ion will decrease. So how will the system respond? If you suddenly decrease the concentration of hydronium by adding hydroxide, then which direction will the equilibrium shift? Will it shift to the right or shift to the left? Remember Le Chatelier's principle? Whatever you do to the system will try to do the opposite, right? So if you all of a sudden decrease the concentration of hydronium, then what will the system, how will the system respond?
We'll try to increase it.
We'll try to increase the hydronium. So which direction will the equilibrium shift? In order to increase the concentration of the hydronium. You sure about that? It will be to the right, because if you decrease the concentration of hydronium, the system will shift to the right in order to increase the concentration of hydronium, right? And according to the question, in an acid solution, the color is blue. So what does that tell us? No, I'm sorry. In a basic solution, when you add base, the solution is yellow, right? So we add base, it decreases the concentration of hydronium, the reaction shifts to the right. So therefore, what does that tell us about the color situation of IND minus and HIND? If the solution is yellow when you add sodium hydroxide, then what's the yellow color due to? Is it due to the HIND or is it due to the IND minus? Remember, the equilibrium is shifting. The equilibrium is shifting in this direction, right? When base is added. So base is added. When a base is added, the equilibrium shifts to the right. And the solution becomes yellow. So what does that tell us about the colors of the different species in there? Which species would you expect to predominate under these conditions, where the base is added?
Ln minus.
I'm sorry?
Ln minus.
IND minus. Okay, so basically what that tells us is that the IND minus would be yellow, right? And then it says it's blue in 0.1 molar hydrochloric acid, which means that it shifts in the other direction when acid is added. Right? So what does that tell us? If it shifts in another direction and the solution becomes blue as a result, what does that tell you about the color of the HID? The color will be what? Will be blue. All right? So this is how this indicator works, right? In an acid environment, it becomes blue, and that's because the HIND is blue, right? That molecule predominates because when you add acid, you're increasing the concentration of H2O plus, you're shifting the equilibrium to the left, which basically favors the formation of the HIND, which has a blue color because that's what the question says. It's blue in 0.1 molar HCl. And then the yellow is due to the IND minus because when you remove the hydronium ion, when you add the base, it shifts to the right, favoring the formation of the IND minus, and therefore the resulting solution is yellow. Okay, so with that said, the next question is, what is the pH at the transition point of this indicator? Now to answer that, we have to look at the values given. Let me just, let me clear everything here. And let me scroll down. Oh, okay, here it is. So it says, what is the pH at the transition point of this indicator? And they gave you this here, which is the range over which the color change occurs, the pH range over which the color change occurs. So what do you think is the pH at the transition point? Well, the transition point would be smack in the middle of that range, right? So how would you calculate that middle value? How would you determine the value that is right in between, smack in the middle of that range?
3.6 plus 5.2 divided by 2.
Exactly, 3.6 plus 5.2 divided by 2, whatever that gives. 4.4, yeah, that sounds right. All right, so the answer here would be 4.4, right? And the question is now asking, what is the pKa for this value, for this indicator, I'm sorry. What is the pKa for this indicator? Well, Ka is equal to the concentration of H plus or H3O plus times the concentration of IND minus, divided by the concentration of HIND, right? Now, at this transition point, these two would be equal to each other. This would be equal to this, right? So that means that the Ka would be equal to the concentration of H3O plus. So therefore, the pKa would be equal to the pH. So what that means is that this value here would be the same thing as that value at that point of the transition. So the next question is, what is the Ka for this indicator? So how would you calculate the Ka for this indicator? Well,
H3O. With the concentration of H3O.
okay. How would you calculate that? Does this look familiar to you? Ka is equal to 10 to the minus pKa, or concentration of H3O plus, since you asked that question, would be equal to 10 to the minus pH. Does that look familiar? If you're given the pKa value, this is how you get the Ka. If you're given the pH value, this is how you get the concentration of H3O plus. So in this case, it would be 10 to the minus 4.4. So on my calculator, I would do 4.4 minus and then shift 10 to the x. So according to my calculation, this works out to be equal to, okay, so that is 1 decimal place. So this needs to be 1 sig fig. So this would be 4 times 10 to the minus 5, excuse me. 4 times 10 to the minus 5, I wrote. 4 times 10 to the minus 5 would be the answer, all right? Okay, let me clear this, because I need to scroll down. Okay, now for this one, okay. Can somebody remind me, I don't want to scroll back up. Can somebody remind me what the pH range is? 4.6 to 5.2. Oh, 3.6 to 5.2, okay. Because we need that information to answer these questions. And what was the colors again? The color of HIND was what? Blue. And IND minus is yellow? Okay, yeah, we need that information as well, okay. So we need this and we need the pH range, right? So the question is, at pH 2.2, this indicator is the color blank, so you need to tell what the color is. And it says the HIND is either greater than, less than, or equal to the concentration of IND minus. Okay, so 2.2 is definitely less than 3.6, right? So therefore, we're talking about an acidic, definitely acidic solution. And we said that below 3.6 or 3.6 and below, the color of the solution would be blue, right? Because that would be indicating that this molecule predominates. So therefore, the answer here would be blue, right? And because HIND predominates, that means that its concentration would be greater than the concentration of IND minus, all right? So that's the answer for F. Okay, so if you understand that, then what would be the answer for G, where it says that the pH is 7.0? So if the pH is 7.0, what would you expect the color of the indicator to be? Anybody? If the pH is 7.0, remember the pH range is 3.6 to 5.2. 3.6 and below, the color would be blue. 5.2 and above, the color would be yellow, all right? So 7.0, the color would be what? Yellow. And what would be the relationship in terms of the concentration of HIND to IND minus? Would it be greater than, less than, or equal to? Less than, exactly. Or, sorry, let me put that here, all right? Okay, 11.3. What's the color of the indicator?
Yellow.
Yellow. And what would be the relationship here? Would HIND be greater than, less than, or equal to IND minus? Less than. Okay, very good. All right. I says at pH 4.4, this indicator, the indicator is the color what? Now remember, at 4.4, the concentrations of both the acid and the conjugate base of the indicator would be the same, right? So what would you expect the color to be? If you have yellow molecules and blue molecules in equal amounts in the same solution, right? Exactly. And this would be equal, right? Because the concentrations of both of them would be equal. So let's put equal here, less than there. Okay. At 4.3, at pH 4.3, this indicator is the color what? Well, you'd expect it to be blue, excepting that, and let me just show you what I said here. It depends on the ratio of the HIND to ion minus. If it's greater than or less than 10 or equal to 10, then the color of the acid molecule will predominate. If the ratio is less than or equal to 10, then the color of the base will predominate. So in the case of, going back to the question, in the case of this one right here, the difference here would indicate that the ratio is still close in terms of the concentration of the HIND to the ion minus. So I would still say that the color here would be green because you don't have an overwhelming predominance of one over the other. So this would be green. But because the pH is lower, I would say that the HIND is slightly less. I'm just going to put less than sign compared to the IND minus. All right? Okay, any questions about that? Any questions? Yes, sir.
Would it be the other way around for the HIND and the IND minus?
Yes, thank you. Yeah, it will be the other way around, right. So this would be greater than. All right. Okay. Any other questions about this? Because I need to scroll down to K and others. All right, let me clear this. And let me scroll down. Okay, now in this case here, it says, oh, I erased what I was using as my guide. Anyway, you guys can help me out. So it says in 0.001 M nitric acid solution, the indicator color is, well, okay, I can say for sure that because this is an acid solution, that means that the concentration of HIND will be greater than that of the IND minus. And the color, what was the color of the acid molecule, HIND? Blue. All right? And then in the case of potassium hydroxide, it would be the opposite, in that the concentration of the HIND would be less than the concentration of IND minus, which means that the color would be yellow in that case. And that would be the answers for those two. All right? Okay, any questions about this? Any questions? Any questions? All right, I think, okay, so that's as far as we can go based on what we have covered so far. Okay, so let me go here. Let me clear this. Let me. What did I do? Okay, what did I do? Oh, all right. Okay, so now we're going to get into solubility equilibrium, dealing with specifically a group of compounds, specifically ionic compounds that are sparingly soluble in water. Now, those of you who have had me in Chem 1 would remember that I gave you a list in Canvas, which is a chart which helps you to make predictions as to whether or not a particular ionic compound is soluble in water, right? In truth and in fact, every single ionic compound has some degree of solubility in water, but those that we consider to be insoluble, their solubilities are very, very small. And you're going to see some representative numbers here shortly, right? A good example of this type of compound would be silver chloride. If you take, let's say a gram of silver chloride and you add it to a test tube of water, a very small fraction of that solid will actually go into solution, right? But when it does go into solution, this is what happens. It undergoes dissociation, right? But what you'll find is that the concentrations of the ions will be very, very small, right? So because you have that equilibrium situation, that back and forth, we can write down an equilibrium expression for it, which as you can see here, is KSP is equal to the concentration of Ag plus times the concentration of Cl minus, right? Because silver chloride itself is a solid, it does not appear in this equation, right? And there's a special name given to this equilibrium constant known as KSP. It's called the solubility product constant. In some textbooks, they just call it the solubility product, right? So KSP is equal to, or the solubility product is equal to basically the product of the concentrations of the ions in a solution of a sparingly soluble ionic compound. Here's another example, magnesium fluoride undergoes the dissociation as described in this equation. And you can write down a KSP expression for that, which is, as you can see there, KSP is equal to the concentration of magnesium times the concentration of the fluoride ion squared, right? And of course, as you can see, here's another example. In this case, silver carbonate, it dissociates as shown, and you see right next to it the KSP expression. So of course, the KSP expression is dependent on the type of dissociation that the particular compound is undergoing. All right, here's a third example, calcium phosphate, and here's a KSP expression, right? So basically, it's very similar to the other case that we met before. The only difference is that we're only concerned with the ions that are formed, and therefore you raise the concentration of those ions to their coefficients in the KSP expression, all right? So as I said before, these compounds are sparingly soluble, right? But we can make predictions based on the concentrations of the ions that are mixed together, we can make predictions as to whether or not a solution will be formed, or if you observe a precipitate coming out of solution. And of course, we go back to our reaction quotient, Q, right? And we compare Q to the KSP in this case. If Q is less than KSP, that means that there'll be no precipitation, right? So therefore, you're just basically going to have a solution which is unsaturated. Now, if Q is equal to KSP, then we have what is called a saturated solution, right? But if Q is greater than KSP, then basically you're going to have a supersaturated solution, which is very unstable, and therefore you're going to have the spontaneous formation of a precipitate as a result, all right? So we can use this as a guide in terms of making predictions as to whether or not a precipitate would form as a result of mixing two ions that can potentially form a precipitate. The precipitate formation is basically based on how concentrated the ions are formed upon mixing, all right? So just to give you some ideas to the type of numbers we're dealing with when it comes to KSP values, right? We have a list here, and again, I have a table that I've published in Canvas, solubility product constants, which is even more comprehensive. And what you'll find about these numbers here when it comes to solubility products is that they are very, very small numbers. In fact, the largest number I can identify here just by glancing right here is for lead 2 chloride. I think that's the largest one. Lead 2 chloride. And the value for that is 2.4 times 10 to the minus 4, right? And that's the largest value, right? The smallest one, what's the smallest one? The smallest one I can identify from this list here, I think it is mercury sulfide, 4.0 times 10 to the minus 54, right? So we're dealing with some very small numbers, and these numbers reflect the fact that these ionic compounds have a very low solubility when you add them to water, right? Okay, so that's basically, and these values are normally quoted at 25 degrees Celsius. Okay, so when it comes to solving problems involving these types of compounds dissolved in water, there are a couple of ways you can approach it. Let me hide this here, get this out of the way, right? But first, let me define a couple of terms. The first one is molar solubility, which is the moles of solute that is dissolved in a liter of a saturated solution. And then we have the solubility, which is the grams of solute dissolved in 1 liter of a saturated solution. So you may be given a question where you're asked to find the KSP of the compound, and you're given the solubility, which would be the grams per liter. You'd have to convert that to moles per liter, and then based on the stoichiometry of the dissociation, you can determine the concentrations of the ions, the cations and the anions, and then you plug those values into the KSP expression to get the KSP of the compound. Or you could be given the KSP to begin with, and you're asked to find the solubility, and basically you're doing the reverse of what you were doing up here, all right? And I think the next slide has a couple of examples of, one type of problem or the other, all right? But this is basically the way we go about solving these kind of problems. So here is an example. What is the solubility of silver chloride in grams per liter? So what you'd have to do is go to the tables and look up the KSP value for silver chloride. And if you look it up, you'll see that it's equal to 1.6 times 10 to the minus 10, right? So the next step would be to set up your ice table. But first, you'd have to, let me see here. Oh, you have to make an assumption. Well, not an assumption, but you don't know what the solubility is, so you have to call it something. So we can call it S, right? So initially, you would have no silver ions and no chloride ions present. If S is the solubility of silver chloride, that means that the change as far as the silver ion is concerned would be plus S, and that for the chloride ion would be minus S. So let me just put a little note here to say that S is equal to the solubility, or I should say the molar solubility, to be more specific, all right? So if S is equal to the molar solubility, then the change in concentrations for silver and the chloride ions will be S and S because of the 1-to-1 ratio between them. So by the time you get to the equilibrium state, the concentrations of the silver and the chloride ions will be S and S, right? So we plug them into the KSP expression, which is this right here. KSP is equal to the concentration of silver ions times the concentration of chloride ions, and then you just put the S values in. Ksp is going to be equal to S squared. So to get S, the solubility, the molar solubility, that would be equal to the square root of Ksp. So we put the Ksp value here, which is 1.6 times 10 to the minus 10, and we get 1.3 times 10 to the minus 5. But we cannot stop there because the question is not asking for the molar solubility. The question is asking for the solubility in grams per liter. So what that means is that you have to take the molar solubility and multiply it by the molar mass of silver chloride. Of course, you know how to do that by now. And then you do your number crunching, and you're going to end up with your answer being 1.9 times 10 to the minus 3 grams per liter. And that's basically how you find the solubility, starting with the Ksp value. All right? Okay. Any questions about this? Any questions? Any questions? Any questions? Okay. I think I have an example of the reverse. I could be wrong. Let me see here. Oh, no, I don't have it. Okay. Okay, I thought I had an example of the reverse situation. I think there may be one or two questions in the assignment which deals with that. Before we get to that though, let me talk about what we have here on the screen. Basically, this is showing you the relationship between Ksp and molar solubility. And basically that relationship is dependent on the type of dissociation or the stoichiometry of the dissociation of the ionic compound. So we just looked at silver chloride in the example that we were working a while ago. And you see that Ksp in that case is equal to the solubility squared, or alternatively, the solubility will be equal to the square root of Ksp, the Ksp value, right? The same will be true for this compound here, BaSO4, barium sulfate, right? This would have a similar relationship between the Ksp and the solubility. And the reason why is because of the 1-to-1 ratio between the anion and cation when it dissociates. On the other hand, if you take a compound like silver carbonate, right, which dissociates in a way such that you have 2-to-1 ratio between the cation and the anion, the Ksp expression is different, as you can see here. Ksp is equal to 4s cubed, or alternatively, S is equal to the cube root of Ksp divided by 4, all right? I think there's some formatting issues with this here, because this should be where you see the letter A and B here. This should actually be parentheses, right? So please make a note of that. The A and B seems to be something that the computer just spits out. All right. So as you can see, in each of these cases, the Ksp to S relationship is dependent on the dissociation or the stoichiometry of the dissociation. All right. I think I'm going to stop here for today because the next slide is an example which will take some time. However, I want you to see if you can do question 3 and 4 and 5, based on what we just covered just now. All right, questions 3, 4, and 5. All right, so that's pretty much it. So I'll see you guys next Monday. Wednesday is your test. What did I say your test is based on? Going by the assignment numbers. I think you're right. Let me just check. I'm not making notes here. 3 and 4. So 3 was equilibrium, 4 is acid and basic. All right, so make sure you review those and make sure you review the assignment keys and so on. All right. Okay.
Really difficult. I have no idea what's going on in half.
This is like harder than my calculus.
Dude, I've been talking with people who are in the other lecture, apparently we have the easy.
Really?
Yeah, the other one has taken like 2 or 3 tests already.
Okay,
So
but I
you know
can't complain,
So
but
you know what, and apparently we have a curve. I don't know if you've looked in the grade book on like a computer, cause I know on the side it has a bunch of like the specific stuff. It says there's a curve that's right now is 0 out of 14%.
listen, I accidentally got somebody's graded test. So I know who like got like the lowest grade
Oh,
on the test the last time, which was a 9%.
what did you get on the last test?
I don't wanna say, it's so
I
embarrassing.
got a 69%. I don't know how I got that high.
Yeah, you got higher than me, but Maria, not Maria, but Aaliyah, she got like an 80 something,
Damn.
right?
She needs to like tutor us or something. That's crazy.
I mean, like when I'm in class, like I get it, but you sit me down with word problems and I'm like, what the?
It's hard, dude. I was making up formulas.
I'm like, this isn't terrible, like this one isn't bad, like I get like the pH and stuff.
Yeah. But, God, that was. You know what? When I saw my test score, I cried tears of
Oh,
happiness.
I'll see you in class.
Right. Yep, I didn't realize that today was Sash Wednesday. And I've been living in this country for too long. Okay, let's me get out of this here. Okay, where's this mouse? Okay, for those of you out there in Zoom, I'll be signing off right now.